All right. Well, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class and these students. Just ask you to bless our work today, help us to glorify you we do, and just understand a little more about systems of differential equations. Lord, in your name I pray, Lord Jesus. Amen. So, I probably should talk about the theory for systems of differential equations for a bit before we do any more examples. So let's just talk about theory for linear systems of ODEs. All right, so last time I told you guys the problem we're considering is essentially, I'll use an R vector this today. So dr dt equals to AR, all right? And so we're going to consider here R is an n vector of functions we don't know, all right? And generally speaking, we could also have another term over here, a forcing function. So here, A is a n by n matrix constants, all right? So we're only looking at the constant coefficient problem, all right? And here, R, typically we would use something like, x1, x2, xn. So these are unknown functions we'd like to find, right? Finding these functions is tantamount to solving the differential equation. Here, f is a vector of functions, right? Generically speaking, and if f is identically equal to 0, then star is homogeneous. Otherwise, else star is non-homogeneous. So I'm calling this equation up here star, all right? So what do we mean by a homogeneous solution? So like definition, if dr dt is just equal to AR, then R is homogeneous solution to star. All right. And so what we want to describe is that this nth order problem, we're going to build the solution from n independent homogeneous solutions, and then also a particular solution. So this kind of sounds familiar, doesn't it? So first of all, we need a definition. So suppose we have R sub I mapping from, let's say, R to Rn for I equals 1 to, say you got k of them, then if C1 R1 plus C2 R2 plus plus, let's just talk about, we're really only interested in n, so I'll go, I guess I shouldn't, I'm sorry, I'll make a decision eventually here. CK RK is equal to 0 implies what? C1 equals to C2 equals to CK equals to 0. Maybe instead of this then here, I should put an and. That's probably better grammar. And if this implies that, then the set R1, R2, Rn is linearly independent. All right. So we can consider linear independence of the vectors of functions. All right. So, all right. So this, to be more fussy, we're talking about a linear combination of functions. So you should understand we could add a t dependence here. All right, so let me give you an example, just so it's a little bit less opaque. I could have R1 is like e to the t, e to the t, and I could have R2 is like 2e to the t and 3. All right. These two functions, really vectors of functions, right? These are not linearly dependent. So like, it's pretty clear that R2 is not equal to a constant times R1, right? So therefore, R1 and R2 is a linearly independent set of functions. That same argument that I went through before, I think, maybe in here. Oh goodness, I can't remember which class I was teaching. But there exists a class this semester that I proved that if you have two things, they're linearly dependent if and only if one is a multiple of the other. All right, so because I can't write R2 as a multiple of R1, these are not linearly dependent. They're linearly independent. These would be genuinely separate solutions to a problem if they were both solutions. All right? Now, so is there some other kind of like nice test we can do to check for linear independence? What do you think? How about this? We'll take this equation right here. All right, you got it? And we'll take that and rewrite it as R1, R2, let's put k equals to n. Rn, this matrix times the vector c1, c2, cn equals to 0 vector. So what I'm doing is I'm supposing we take these n functions, glue them together. So I'm gluing my n vector vectors and vector valued functions into a single n by n matrix of functions, all right? So I've got this matrix of functions times this constant vector equals to 0, all right? Linear algebra tells me then that the only way I can get only the 0 solution for this, right, is if that matrix of functions is in fact invertible. There's a simple test for that. So I need that this needs to be, I need this to imply that the constant vector is just the 0 vector, right? That's linear independence. So if I want the columns making up this matrix here, if I want this to be an invertible matrix, there's a simple test, right? So if the determinant of this big old matrix is not equal to 0, then the set R1, Rn is linearly independent. This is even easier than our previous discussion of Wronskian. Like before, we had to take the defining linear independent equation, differentiate again, n-fold times, n-1 times, regroup all those equations into a single big old equation, and argue, hey, that the determinant of that matrix must be non-zero for linear independence, right? That defined the Wronskian for us. Here, the Wronskian is way easier. The Wronskian, in this context, is simply the determinant. Right here, this is the Wronskian. Wronskian of vector function R1, R2, Rn at time t is simply the determinant of the matrix formed by gluing these things together. So like for my example 1, we could straight up calculate the Wronskian. It would be very boring. Here's how it goes. So example 1, Wronskian. So I'm using the word Wronskian in a new way, guys. Oh, well, this is the example 1 Wronskian, though. So, so if you would like, I can put an example 2 there. There you go. So we're calculating the determinant simply of e to the t, 2e to the t, and 3, right? Which I just made up. So you guys know how to calculate determinants, right? So what is it? Uh-huh. So I heard it. We got a 3e to the t minus 2e to the 2t, say, right? So there you go. That's the Wronskian. All right. Okay, so that's what we mean by linear independence of vector-valued functions. It's just like we defined before. They can't just simply be scalar multiples of each other, something like that, all right? We want to find genuinely independent functions. Now, here's the theorem. Star has solution R equals to RH plus RP, where R sub H is equal to C1 R1 plus C2 R2 plus plus Cn Rn, and dr sub I dt is equal to A R sub I for I equals to 1 to at the end. And by the way, R1 all the way out through Rn is linearly independent. And drp dt is equal to A times Rp plus what? So I'm saying Rp is the particular solution. It actually solves, remember my star has that plus F term. So it actually reproduces this pesky inhomogeneous term like that. All right? And that's the general solution. I should probably weasel a word in here, general solution. So that covers all possible initial conditions. All right? And there's some more terminology I should tell you guys, because these things you need to know. There's a name for this set of homogeneous solutions which is linearly independent. If you have a linearly independent set of homogeneous solutions, such a solution is called a fundamental solution set. Fundamental solution set is a set of n linearly independent solutions to the homogeneous problem for a given matrix A. All right? Now, I'm not going to prove this theorem because, you know, that's not what this course is really about. But we're going to learn how to use it. I will give you a partial proof. Check this out. So, if you assume that we have these n homogeneous solutions, right? And I look at dr dt as ddt of my sum I equals 1 to n of ci ri, so that's my homogeneous part of the solution, plus rp, right? So this is the sum I equals 1 to n of ci dri dt plus drp dt, all right? So what does this give us? Remember, they're the homogeneous solutions. So each one of those gives us A times Ri, right? So we have, the sum I equals 1 to n of Ci A times Ri. And then plus what? Well, this here, what's drp dt equal to? by assumption, drp dt is equal to ARP plus F. So I have A times the particular solution plus F. All right? And then I use properties of matrix multiplication to pull the multiplication by A back out of the sum, and pull the scalar multiplication back in. And I'll leave the F out there by its lonesome. So I have A times the sum, I equals 1 to n of Ci Ri plus Rp, close parentheses, plus F, right? But that's exactly A times my proposed solution, R, plus F. So you see, if we have homogeneous solutions as advertised, and we have a particular solution as claimed, when we plug it in and work out the differential equation, you see it works, right? dr dt is A times R plus F, which is tantamount to solving star, all right? So there's a couple of obvious questions here, right? Like number one, how do you find this fundamental solution set, right? And number two, how do you find the particular solution, right? These questions hopefully sound familiar to you. These are the questions that we faced in the last story arc of the course, right? I mean, same questions. So these are the questions that we need to settle. Number one, how to find n linearly independent solutions to dr dt equals to AR, right? And number two, how to find the particular solution which solves drp dt is equal to A times Rp plus F, all right? Once we achieve those two goals, then we've found the general solution and we can solve any linear system, all right? Now, we're not going to look at the particular solution question today. We put that off for later, just like we did before. First, we solve the homogeneous problem. Then later, we solve the particular solution problem. It's also helpful for us to introduce another idea, which is called the concept of a solution matrix. And so I'm going to try to reinforce that concept as we work examples today. But in order to do that, I probably better first introduce the concept, right? So what's a solution matrix? This is going to be really, really surprising. A solution matrix is a matrix of solutions. All right, so like here's how that works. If I have a big X, which is R1, R2, Rn, where dri dt is ARI. In other words, each column of this matrix is a homogeneous solution to dr dt equals to AR. Then what's the deal? What's dx dt? How do we differentiate a matrix? We talked about this last time, right? This umbilicus is going to have its way. At some point, I'm going to flatten my butt, and it's going to be bad. It's going to be real bad. But you guys will laugh, so it'll be worth it. Say, no, we won't laugh. We're good students. We wouldn't celebrate your demise, right? 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 Yeah. Okay, right. Remember, so we differentiate column-wise or component-wise, like this. Yeah? So the differentiating the matrix is to differentiate each column of the matrix. And as such, each column gives us A times R1, A times R2, A times Rn, like that. And then, from linear algebra, there's a very important matrix identity to know about here, which is that you can factor A out of this column by column product, all right? So you can the way matrix multiplication works, I can actually factor A out, like so. And if you look at that, then what we have is what? This is x again, right? That's the solution matrix again. So what do I have? I have dx dt is equal to a times x. So this is like a little theorem. If you have a matrix which column by column is a solution to the homogeneous problem, then the matrix itself solves the analogous matrix differential equation dx dt equals to ax. By the way, this calculation is reversible. If I have a matrix which solves the matrix differential equation, it correspondingly has every column in that matrix must be itself a separate, must be a solution to the homogeneous problem. All right. So that's something to remember. Now, furthermore, what would we mean if we had a fundamental solution matrix? What would that be? What would a fundamental solution matrix be? So definition, X is fundamental solution matrix. I can't spell matrix for dr dt equals to AR if X is solution matrix such that the determinant of X is not equal to 0. In other words, a fundamental solution matrix is an invertible solution matrix. More to the point, a fundamental solution matrix has linearly independent columns. So a fundamental solution matrix is in one-to-one correspondence with a fundamental solution set. You give me a fundamental solution matrix, I can give you a set of fundamental solutions, and vice versa. So what we're going to do in the remainder of class is we're going to solve problems using the eigenvector technique I introduced last time. And each problem that we solve, we're going to find a fundamental solution matrix. All right? So let's do it. So I'll remind you guys, what was the story about the eigensolution? We said if we want to find a solution to dr dt equals to AR, we can look at the characteristic equation. We can find the solutions to the characteristic equation. Those solutions are called eigenvalues. And the corresponding vectors are called eigenvectors, and those give us actually solutions to the differential equation. All right? So let's see here. Example 3. Suppose we're going to solve. I was going to give you like a really, really stupidly easy. Let me make a only slightly stupidly easy, but not the stupidest of stupidly easy problems. Here goes. So let's try to solve dr dt equals to AR, where A is equal to -4, -1, 5, and 2. So let me just pull back and remind you guys that where this would have come from. This would have come from like dx dt equal to like -4x minus y, and dy dt equal to like 5x plus 2y, right? And we are thinking of my vector of unknown functions as like x and y here. That's my notation for this problem. So how do we find the fundamental solution set here? All right, so here we go. We first of all calculate eigenvalues. And to do that, we look at the determinant of A minus lambda I. So here, that looks like the determinant of -4 minus lambda, -1, 5, and 2 minus lambda. So lambda times the identity here, guys, is simply a 2 by 2 matrix that looks like this. All right? So do you see what I'm doing? I'm just subtracting lambda off the diagonal entries. Do you guys see that? That's it. Now this formula I just wrote down, when we set that equal to 0, that's the characteristic equation. So, okay, we can do this. And I'm going to do a standard trick, which is to get rid of the minuses. See if you can follow what I did here. You see what I'm doing? If I'm multiplying this by that, I can factor a minus out of each and just cancel the minuses, because why write 3 minuses when we can just write 1? You know? Be careful with minuses. They'll get you. And then, of course, the other minus is from the determinant, right? AD minus BC, so the minus BC becomes plus 5. All right, great. Now, I'll multiply this thing here out. I got myself a lambda squared, plus 4 lambda, minus 2 lambda is plus 2 lambda, minus 8 plus 5 is minus 3, I think. And, hey, that factors. All right, so what we got here? We've got lambda plus 3 times lambda minus 1. So I put that equal to 0. That's the characteristic equation. I get lambda 1 equals to, say, minus 3, and I get eigenvalue 2 equals to 1. It doesn't really matter which one you label 1 and which one you label 2. I just made a choice. All right? A lot of software will enumerate them from largest magnitude negative to largest magnitude positive. That's a pretty standard convention for how to label the eigenvalues, but I do not dogmatically stick to that. So those are eigenvalues. Now to find the eigenvectors, I want to solve, for lambda 1 equals to minus 3, I need to solve a plus 3i times u1 equals to 0. That would be the equation that the eigenvector u1 should solve. So let's plug that in here. I take my matrix A, I add 3 times I to it in this case. That gives me minus 1, 5, and 5. All right? And for u1, I'll use variables u and v. These are disposable variables that I use to figure out what the components of u1 are. Do you see what goes on here? Look at this. This is what should happen for us, all right? Because the eigenvalue problem is a problem with infinitely many solutions, it must not be the case that the 2 rows are genuinely distinct. If they are, that means there's only the 0 solution, which would mean we're wrong. We must find a non-zero eigenvector. But you see, these 2 equations are really just the same equation. So I can just keep either one of them to solve it. I like the first one. First one translates to, like minus u minus v equals to 0. So I might as well say v is equal to minus u, right? And lo and behold, u1 is equal to like u minus u, or if you like, u times 1 minus 1. So you can pick anything you want for u. Every possibility is possible except 1. What's the one thing I can't make u equal to? 0, right? Lambda 2 equals to 1 means I'm looking at a minus I times u2 equals to 0, which gives me the matrix problem minus 5, minus 1, 5, 1 times the vector uv equals to 0, 0. Once more, you can see that we have the same equation twice, right? Pick whichever one you want. Minus 5u minus v equals to 0. I'm going to solve for v is minus 5u. So therefore, my u2 is like u and minus 5u. I can factor the u out. I've got any multiple of 1 minus 5. Right? Now this idea of writing the arbitrary eigenvector gets old really fast. So what we're going to do as a matter of practice is we're going to pick a token solution, all right, for each eigenvalue, if there's just one to be picked. It may be that we'll have two different independent eigenvectors for a given eigenvalue. We'll see that later. But for here, let me, I need to work myself up into the corner. I think we got enough room. So what I'm going to do is I'm just going to put u equal to 1 for both of these, and I'm going to write down the solutions. So going back to what we did last time, I find that my solution has the form c1 e to the minus 3t times u1, which was, we're just going to use 1 minus 1, plus c2 e to the t times my eigenvector with eigenvalue 1, which was 1 minus 5. And there you go. That is the general solution to this differential equation, just like that. Solved. Now we could go back to the scalar variables. I could write down this is the vector solution, all right? General vector solution. What would the scalar solution look like? If I wanted to write down the scalar solution, what would that be? So I would be talking about x and y, right? So we'd have what? We'd have x equals to like c1 e to the minus 3t plus c2 e to the t, and y is equal to minus c1 e to the minus 3t minus 5c2 e to the t, right? This right here would be the general scalar solution. Now, oftentimes, I just ask for the general vector solution. In fact, if I don't say otherwise, if I just say solve the system of differential equations, it is our custom to simply write the vector solution, because it is straightforward how to get to the scalar solution once we have the vector solution, right? So why go through all that? It's not particularly interesting. I mean, it's important if you're actually solving a given system for some application or something, to be able to undo the vector formalism to get back to the scalar solutions, right? You might need them to code something about some machine or something you're working on. I don't know, all right? But any questions? I'm referencing something we did last class, so if you don't know what I'm doing, let me remind you. We derived something last class, end of class. We derived that what we derived was if r equals e to the lambda t times u has lambda as a solution of the determinant of a minus lambda I equals to 0, and a minus lambda I times u is equal to 0, then R solves dr dt equals to AR, right? That's the basic theorem that we're working with here. That's what's the driving force of my example. I find the eigenvalues by solving the characteristic equation. I find the eigenvectors by solving a minus lambda I equals to u. And then, provided I have enough eigenvectors, I have solved the problem, right? I said I would be looking at the fundamental solution matrix as we went on. Can you guys tell me what would the fundamental solution matrix be from my previous example there? So we had, you know, for example, what was it, example 4? Yeah. For example 4, I had basically R1 was e to the minus 3t times, 1 minus 1? Is that right? And if you look at it, I didn't write these down, but these are implicit. R2 was e to the t times, oh man, I can't remember. What's that, 1, negative 5? Okay. So the fundamental solution matrix that this would give us, R1, R2, like this, right? That would be, you know, like e to the minus 3t minus e to the minus 3t, e to the t, and minus 5 e to the t. So there you go. That would be an example of a fundamental solution matrix. I would point out that our solution that we wrote down, right? You could write it like this. R of t is equal to x times the column vector c1, c2, right? This is another way to write our solution. We could express the general solution as the fundamental matrix times a vector of constants we don't know, right? How would I know that vector of constants? I would need additional information, right? We'd have to have an initial condition for the system to fix those constants. Okay. Let us look at another. Example 5. Suppose we're going to solve x prime is equal to 3x minus y, and y prime is equal to minus x plus 3y. I hope this works out nice. I just made it up. All right, let's see what happens. Listen, if it gets too ugly, I'm going to use technology. All right? So here we go. First of all, I need to figure out what the matrix is. Here, the matrix is what? I got myself a 3, minus 1, minus 1, 3. All right? I don't know if I talked about this with you guys, but do you guys know what a transpose of a matrix is? So transpose, if we transpose a matrix, like if I take, say, A, B, C, D, and I transpose it, the way that works is I leave the diagonals alone, they just stay put, and the off diagonals, they flip-flop. All right, that's the transpose of a matrix. This matrix is an example of what's called a symmetric matrix. All right, this is a symmetric matrix. Let me tell you a little secret about a symmetric matrix. It has A transpose is equal to A. That's the definition of symmetric. There's a deep theorem of linear algebra that says that a symmetric matrix has real eigenvalues. And not just that, we can pick the eigenvectors of a symmetric matrix so that they're orthogonal, so that they're perpendicular, and we can make them length 1. So eigenvectors for a symmetric matrix are super nice. So I know this problem has a nice answer, is what I'm trying to tell you. So let's calculate the eigenvalues. We need to do what? Look at the determinant of A minus lambda I. So that's the determinant of 3 minus lambda, minus 1, 3 minus lambda. This is lambda minus 3 quantity squared, minus 1, which we can factor as such by the difference of the squares formula. I don't know if you know this, but 1 is 1 squared, right? So this is the difference of squares. So difference of squares plus, difference of squares minus, A plus B. Anyway, so what this gives me is lambda minus a 2 times lambda, oh man, dudes. One of those has got to be a minus, sorry. Lambda minus 2, lambda minus 4. Okay, don't worry, if we had gone on, here's the thing, if you factor this characteristic equation incorrectly, what happens is when you try to go find the eigenvectors, you won't get infinitely many solutions. You'll get a single solution. It'll be the 0 vector, and that's your hint that you are not working with an eigenvalue. You've solved the characteristic equation wrong. But hopefully we didn't do that. Let's go on. All right, so eigenvalues are 2 and 4. Let us look at lambda 1 equals to 2. So what I have to solve is a minus 2I times u1. For the current problem, that is 1 minus 1 minus 1, 1 times uv, all right, equals to 0, 0. So, all right, apparently I need what? I need u minus v equals to 0. So therefore u is equal to v. Hence, let's make our u1 equal to, let's just go with 1, 1. You know, that'll do it. You can always check your answer. Does it work? If I put 1, 1 back over here and I calculate this matrix product, it works because 1, 1 is perpendicular to 1 minus 1 and 1, 1 is perpendicular to minus 1, 1, right? The dot product of my eigenvector is 0 with both rows. That must be the case if we're solving the equation correctly. Then what? Oh, lambda equal to 4, right? Lambda 2 equal to 4. We have a minus 4i times u2. All right, so I have to subtract 4 off the diagonal. So 3 minus 4 is minus 1, right? My minus 1, my minus 1, my minus, well, this is very boring. Minus 1, minus 1, minus 1, minus 1. All minus 1s all around. All right. So what are we up against here this time? Looks like we're up against a minus u minus v equals to 0, which gives me that, you know, I don't know, however you want to do it. U equals to minus v, let's say. Right? If I put u equals to minus v, I usually put v equals to 1 in this context. And so this tells me that my u2 is apparently, you know, minus 1, 1. Now at some point, you guys are going to interrupt me and ask me a question, which is, why did I write that vector down? Right? Why did I write that specific vector down? Why did I choose v equals to 1? If you're looking for some deep reason, you're not going to find it. The answer is because I can. Any choice will do as long as it's not 0. I could put v equal to minus 1. That would just give us the vector u2 is 1 minus 1. If you look at how these vectors play into the solution, you'll understand that all we're doing is redefining the C1 and C2 in the general solution. We always have a flexibility to like redefine the constants in the solution. That flexibility is reflected in our ability to choose any scalar multiple of the eigenvector we wrote down. All right, so like this is just a choice. There is an ad hocness to what I'm doing. And so anyway, the solution here, xy, is equal to C1. My first eigenvalue was 2, so I do e to the 2t times my first eigenvector, which was 1, 1, plus C2, e to the 4t, and then minus 1, 1. And there you go. That is the general solution to this here differential equation. Yeah?
But could you say you could make the u1, u2 solutions anything as long as it's linearly dependent with what we found here?
Yeah, I mean, I could just as well have made this 11, you know? Wouldn't have changed anything. It just would mean C1 means something different, right? But so as a point of order, I just try to make them pretty. There are other reasons. You might want to make the vectors have length 1. All right, and I'll explain more why that is when we get towards the end of class here. But let's look at another example. So not everything is 2 by 2, right? There is also 3 by 3 problems to deal with. And sometimes, even in the 2 by 2 case, like we don't have enough, all right? See if I can find you one of those. Yeah, here, let's look at this one. So far, both of the examples have worked out super nice because we had a system of 2 differential equations and we found 2 linearly independent solutions. We found the general solution. The eigen technique was enough. It was enough. Is it always enough? No, it's not always enough. Sometimes you must do something else. All right, but our first order of attack is always to try to find as many eigensolutions as we can. So this will illustrate the trouble, though. X prime is 3x plus y. Y prime is minus 4x minus y. All right, so matrix xy prime. We've got ourselves a 3, a 1, a minus 4, a minus 1, xy. All right, so you guys figure out what is the determinant of a minus lambda I here. We're talking about the determinant of 3 minus lambda, 1 minus 4 minus 1 minus lambda, right? I'm supposing this up here is a, obviously. So you guys figure it out. What's the characteristic equation this time? Oh man. I've got a lambda minus 3 times lambda plus 1 plus 4, also known as lambda squared, minus 3 lambda plus lambda minus 3 plus 4, also known as lambda squared minus 2 lambda plus 1. That factors, doesn't it? That's what, lambda minus 1 squared. Ah. So this one, we have lambda 1 equals to 1 with algebraic multiplicity 2. All right. Up to now, everything had multiplicity 1, so there really wasn't anything to talk about. This one has algebraic multiplicity 2. However, the geometric multiplicity of 1 is actually just 1. We're going to find that there's only one linearly independent eigenvector to be found here. Check it out. So a minus I times u1 is, we got ourselves a 2, a 1, a minus 4, a minus 2 times uv, 0, 0. So go through the usual song and dance. My u1 is going to be equal to like 1 minus 2. You want to know my secret? I don't actually solve the equations. I just look for a vector which is perpendicular to both of these rows. Let's see, if I put a 1 there and I put a minus 2 there, I get 2 minus 2 for the dot product of this and that, and likewise that. So that works. But yeah, you could go through the equations if you want. Or you can just write down the answer. For a 2 by 2 at least, I can. Always just write down the answer. We should check our answer anyway, right? If it's right, when I put it back over here, it should multiply to give me 0. If it doesn't, I need to recalculate, you know? But that one works. But that's it. There's nothing else, right? But this is a 2 by 2 problem. So it's supposed to have 2 linearly independent solutions. Where's the other one? Yeah? Where's the other one? Now, if you, any ideas? So like my solution here, R1, is e to the t times 1 minus 2. So there's a token solution. I got 1, but I need 2. What would you guys guess is the other solution? What's that? What's it? Just multiply by t? That's a nice idea, but it doesn't work. So we're going to have to come back to this. I'm going to leave it as a mystery. How do we fix this? All right? Obviously, there's something else to be said. We'll have to come back to this. So that's one problem. The other problem with the 2 by 2 problem is we could end up with a complex eigenvalue. All right? So, example 7, if we had x prime equals to minus y, and we had y prime equal to 4x, that gives me a is 0, minus 1, 4, 0, like that. So then I have the determinant of a minus lambda I is the determinant of minus lambda minus 1, 4 minus lambda, which just so happens to be lambda squared plus 4 equals to 0. So you see we have solutions plus or minus 2i. All right. So what do you think we should do? Well, think about it. Think about the calculus we did leading to the eigensolution, right? There's nothing especially real about any of that. It would all still go through if our eigenvalue was complex, because the fundamental thing that was pitting it together was the fact that the derivative of e to the lambda t was lambda e to the lambda t. And we know already from our previous work that that's still true if lambda is a complex number, right? So we should be able to write down a complex solution if we have a complex eigenvalue, right? So let's find the eigenvector. What's it going to look like here? I mean, we're going to have to do some complex arithmetic, all right? So let's do it. And remember how complex stuff worked before? Did we have to do the plus and the minus? Remember, just 1 was enough. So let's pick the plus. Let's look at lambda equals to 2i. And let's try to solve a minus 2ii times u is equal to 0. All right, so what that looks like is minus 2i minus 1, 4 minus 2i uv equals to 0, 0, right? Now that's it's a little bit worrisome at first glance, because it seems like maybe the two equations that we're looking at aren't really different. I mean, they're not the same, right? But it's just an illusion. Notice if you take the first equation and you multiply it by 2i, minus 2i squared, I mean, this times 2i gives me 4. And this times 2i gives me minus 2i. So in fact, to get from the top equation to the bottom equation, simply multiply by 2i. So they're the same equation. We could pick whichever one of them we want to understand the solution. I suggest picking the first one because it's easier. The first one gives me minus 2iu minus v equals to 0, which gives me v is equal to minus 2iu. So I'll pick u equals to 1, because why not? That gives me v is minus 2i. And so apparently my eigenvector, my complex eigenvector, would be 1 minus 2i. And so my solution then, which I'm going to use a z for because it's complex, z vector would be e to the 2it times my 1 minus 2i, right? This is in fact a complex solution to this system of differential equations. But we're not interested in complex solutions. We're interested in real solutions, right? So we need to do the same thing we always do, which is to work out the real and imaginary parts here. So this is cosine 2t plus I times the sine of 2t. right? And then over here we've got, let me write it this way. This is 1, 0 plus I times 0 minus 2, right? We can break that up into the two vectors like that. And then if we multiply this out, what we got here is a cosine of 2t times 1, 0 minus sine of 2t times 0 minus 2 plus I times cosine 2t, 0 minus 2, plus sine 2t, 1, 0. So if you're wondering what I did, I just multiplied it out, and I did one small thing, which was I squared is minus 1, right? I squared is minus 1. The reason I've done all this right here, my friends, is precisely the real part of the complex solution. The coefficient of I here is the imaginary part of the complex solution. What's the general solution, do you think? If you don't mind, I'm going to put the general solution. Well, anyway, this mystery we're not solving today, so I'm going to erase it. All right? It will have to remain mysterious for the time. In fact, it's going to remain mysterious right up until after spring break. So, all right, so here we go. The general solution in this case is C1 times the cosine of 2t times that vector, 1, 0, minus the sine of 2t, 0 minus 2, plus C2 times the other thing, cosine 2t, 0 minus 2, plus sine of 2t, 1, 0. All right? There you go. That is the general solution to this problem. And that's what we have to, anytime we get a complex eigenvalue for a 2 by 2 problem, we can expect the solution looks something like this. All right? That's it. That's everything that happens in the 2 by 2 homogeneous case. Either you have distinct real roots for your characteristic equations, which is like the first two examples I did, or you have a repeated root, and unless the repeated root is really dumb, you're only going to have one solution. All right? What's the dumb example? This one I can solve like stupidly easy. Check this out, you. X prime equals to 9x. Y prime equals to 9y. All right? So this gives me A is 9009. What's the determinant of A minus lambda I here? So therefore, lambda equals to 9 twice, right? What are the eigenvectors of this? How about this? A minus 9i times u is equal to what? 0, 0, 0, 0, 0, u1. So which vectors solve that? Yes, this is a good answer. The answer is everything. We like everything except for one. We discriminate against the zero vector. Sorry. Is what it is. So yeah, the solution then is xy is equal to like c1. I mean, we can. Here's the vectors I would usually use. I would do e to the 9t 1, 0 plus c2 e to